Identify the nature of the reactants. Potassium hydroxide, KOH, is a strong base that dissociates completely in water to yield hydroxide ions, OH to the power negative. Hydrobromic acid, HBr, is a strong acid with a very large dissociation constant, KAGG1, that dissociates completely to yield hydrogen ions, H to the power plus. Because both are strong species, they react completely in a 1-to-1 ratio to undergo a neutralization reaction. H to the power plus plus OH to the power negative gives H2O quad. Calculate the initial moles of OH to the power negative and H to the power plus ions, using the formula moles equals volume, L, times molarity. Initial moles of OH to the power negative equals 0.1500 liters times 0.10 molar equals 0.0150 moles quad. Initial moles of H to the power plus equals 0.0500 liters times 0.20 molar equals 0.0100 moles quad. Determine the limiting reactant and excess reactant moles. H to the power plus is the limiting reactant because there are fewer moles of it, 0.0100 moles, less than 0.0150 moles. During the neutralization reaction, all 0.0100 moles of H to the power plus is consumed by reacting with 0.0100 moles of OH to the power negative. The moles of excess OH to the power negative remaining in the solution are moles of excess OH to the power negative equals 0.0150 moles. 0.0100 moles equals 0.0050 moles. Calculate the total volume of the combined mixture. Combined volume equals 150.0 milliliters plus 50.0 milliliters equals 200.0 milliliters equals 0.2000 liters. Quad. Determine the equilibrium concentration of hydroxide ions, OH to the power negative. Divide the excess moles of hydroxide by the new total volume of the solution. OH to the power negative equals 0.0050 moles over 0.2000 liters equals 0.025 molar. Calculate PO and convert to pH. On Section 1 of the AP exam, calculators are not allowed. However, you can easily approximate this logarithm. Since OH to the power negative equals 0.025 molar lies between 0.01 molar, 10 to the power minus 2 molar, and 0.1 molar, 10 to the power minus 1 molar. Its PO must fall between 1.0 and 2.0. Specifically, PO equals log 0.025, approximately 1.6. Convert PO to pH using the water equilibrium relationship. pH equals 14. PO quad pH approximately 14 minus 1.6 is equal to 12.4. Looking at the options, 12.4 is closest to 12, identifying option D as the correct choice. Why Othong wrong? Option A is incorrect. A student might arrive at this value if they successfully calculated the excess mole value, 0.0050 moles, but misidentified it as excess acid asterisk, H to the power plus, rather than excess base, OH to the power negative. This would lead them to calculate H to the power plus equals 0.025 molar, which yields a pH of approximately 1.6, closest to 2. Alternatively, they may have calculated the correct PO of approximately 1.6, approximately 2, and mistakenly selected it as the pH. Option B is incorrect, for this is a distractor value that could result from severe decimal or mathematical placement errors during the calculation of moles, e.g., miscalculating excess concentration as 10 to the power minus 4 molar, or by confusing the chemical equations with other multi-step polyprotic acid ionizations on the exam. Option C is incorrect, 7. A student might select this value by quickly identifying that a strong base is being mixed with a strong acid and assuming that all strong acid-strong base mixtures automatically result in a perfectly neutral solution, pH equals 7. However, this only occurs when equimolar amounts of H to the power plus and OH to the power negative react. Here, the base is in excess, so the final solution must be basic, pH greater than 7. The correct answer is option D, 12.